Shapley value in unanimity games. First, a brief recap of what we have done in previous lectures. So this is the unanimity function omega s of c, which is given by this expression here. It's defined in terms of a subset S of the grand coalition. And so if the coalition C contains S, then its unanimity function is 1, otherwise it's 0. This is depicted, the first case is depicted here. S is fully contained in C. And this is the second case here where S is not fully contained in C. And we've also seen that the value function of any coalition can be uniquely expressed in terms of the unanimity functions. We have 2 to the n number of unanimity functions, excluding the null. And then we do the summation of this delta S times omega SC. These deltas are called the Harsanyi dividends. And in vector matrix form, we can rewrite the same expression in this form. So consider this game here. These are all the unanimity functions for all the coalitions, A through ABC. And I take all these zeros and ones and place them in this matrix here. And the values are in this vector here. And the Harsanyi dividends, the vector of deltas, is this. Whence I get this expression here, and note this transpose, which is equal to this. V equals omega transpose delta. And solving, we can get the Harsanyi dividends, which are equal to these. Unanimity Shapley value. We'll prove this theorem. The Shapley value of the unanimity game n omega s, where s is some predefined subset of n, is given by this expression. The Shapley value of agent I is 1 over size of S if I belongs to S, and it's 0 if I does not belong to S. So this is the marginal contribution of agent I to this coalition C. If the coalition C contains all the agents in S except agent I, then when I joins the coalition, the value of this coalition jumps to 1, whence the marginal contribution of agent I is 1. On the other hand, if the coalition does not contain all the elements of S excluding I, then the marginal contribution of I is 0. Therefore, let's consider this case here. So this is when I is not a part of S. In this case, the marginal contribution of I is always 0, whence the Shapley value of agent I is equal to 0. So this is the situation where the Shapley value of the agent is equal to 0. That's when I is does not belong to S. Now let's look at the second situation here. All the agents I that belong to S, from symmetry, since their contributions, their marginal contributions are all equal, from symmetry, each agent must receive exactly the same share of the total value, which is actually 1 in this case. Whence each such agent I, which belongs to S, has a Shapley value of 1 over size of S, which is this part. So we proved the theorem. Next, we should show this theorem. For any value function v, the Shapley value can be expressed in terms of the Harsanyi dividends in this manner here. So the Shapley value of any agent I is equal to summation of delta divided by the size of S. Now the summation, note that it's carried out over all subsets S that include agent I as a member. This is the agent I. This and this, neither of them are directly related to I. So the summation here is carried out over all subsets that include agent I. And we will use these following relations. These are the four relations that we shall use. The first, third, and fourth expressions we have already seen. And to get the second expression here, all I've done is replace the value. This is the expression for the Shapley value for any v, and all I've done is replace v with omega s, the unanimity value. And that gives me this expression here. So I have these four expressions. So the Shapley value of agent I is equal to this. This is from the definition of this Shapley value. And now I'll use this expression here. So V of C, I'll just plug in this here. So this is my V of C. And likewise for V of C union I, all I've done here is replace C with C union I. Whence I get this expression here. And so this is where I was, and then I do some simple manipulation. First, I observe that both these summations have this delta common, so I group these together and I have a single summation with the delta here, and then I swap the bring this summation rather here, and so I have this expression here. Next, observe this here. What's inside this parenthesis is the marginal contribution of agent I to the coalition C. And we note that the marginal contribution is 0 if S does not contain agent I. So all I've done here is introduce this I belongs to S here, because this marginal contribution here will disappear when I is not part of S. And so I arrive at this expression here. Next, we do some simple algebraic tricks. First of all, I swap the order of the two summations. And so summation over the subsets S appears first, and followed by the summation over the coalition C. And then I take this delta here because delta is independent of coalition C, and so I arrive at this expression here. So this is where we were at, and then I take the 1 over n factorial inside, and so this is my inside expression within this large parenthesis, and this is equal to this. From this expression that we've seen earlier, this is nothing but the Shapley value of agent I corresponding to the unanimity function omega s. And then we've already seen that the Shapley value of the unanimity function is 1 over S, and so this is the final expression that we have, and this proves the theorem.